This is the instructional video for lesson 1.5, part A. And on your note sheet, please cross off B and correct that for me, please. It should be part A. The objectives for part A of lesson 1.5 are applying the properties of square roots to simplify radical expressions and solving a quadratic equation by using square roots. So we're going to go through a few of the vocab terms that you need to know for properties of square roots, and then we're also going to look at a few of the properties of square roots. So to begin, let's look at the definition of square root. It's a factor of the number under the radical sign that, when multiplied by itself, equals the number under the radical sign. So a factor would be a number times another number, but in this case, it's going to be the exact same number. So for example, if we have the square root of 9, think of a factor of 9, so numbers that multiply to the number under that symbol, but it has to be a number times itself. So of course we know that the square root of 9 is 3 because 3 times 3 is 9. Could we also have negative 3 times negative 3? Absolutely. So the actual square root of 9 is both the positive version of 3 and negative 3. And we want to call the radical sign the radical sign. It's not always a square root. It could be a cube root. So sometimes we'll see a little 3 outside of that, or it could be the fourth root of a number. It could be the sixth root, or any root of it. So for instance, if we had the third root or cube root of 125, that would be 5, because 5 times 5 times 5 is 125. So 5 itself is going to be the cube root of 125 because we'd have to multiply it by itself 3 times to get to 125. So in this case, when we're talking about square roots, it would just be what number times itself just once, 2 times of the number would be the root. Okay, so again, like I used the square root of 9, if I use the square root of 64, well then we know that is 8 plus or minus 8. Okay, because 8 times 8, 2 8s multiplied together is going to be 64. Our final vocab word is radicand. It's the expression or number under the radical. So when we're talking about a radicand, it's the actual number underneath the radical symbol. So if we were taking the cube root of 125, the radicand is 125. If we were taking the square root of 64, the radicand is 64. Okay, so let's review some of the properties of square roots. This may be something that you've seen previously. Hopefully this is just a refresher for you. But the product property of square roots is that numbers underneath the radical symbol can be multiplied. So if we had a times b underneath the radical, we can separate those out and say that the square root of a times the square root of b, notice that there's a multiplication symbol here, is the exact same thing. And vice versa, if we had two numbers underneath the radical symbol, we could multiply those together and combine them into one radicand. Okay, so let's take a look at an example. So if we had the square root of 18, we could think of the factors of 18 and separate those out and say, well, 9 times 2 is 18, and let's make those into two separate square roots. So the square root of 9 times the square root of 2. And we know that there is a square root of 9. The square root of 9 is 3. So we would simplify this to 3 root 2. Okay, let's take a look at the quotient properties. The quotient properties state that if we have a fraction under the square root, we can separate those two numbers and make a square root on the top of the fraction and a square root on the bottom of the fraction, and vice versa. If we had the square root of a number over a square root of a number, we could make that into one radicand and just leave that under the radical symbol as I show here. So if we take a look at an example, let's see if we can do square root of 2 over 25. So that's in the form that we started with over here, And what I would like you to do is realize that you can make this into two separate radical operations. So the numerator is now square root of 2 and the denominator is square root of 25. And that makes it nice because we do know that we can take the square root of 25 and that is going to be 5. So when we take the actual square root, we no longer need the square root symbol. And I want to mention that back up here when we're giving an answer of 3 root 2, whatever we get out of this square root comes outside of the radical symbol. So we no longer need that number under the radical symbol. And I'm going to do a couple of these examples and then leave a few for you guys to do. So thinking of numbers that multiply to 80 in problem A here, it looks like we can find 16 and 5. So the idea is to find some numbers, factors of the number underneath the radical symbol that are perfect squares. And I found that 16 is a perfect square, so therefore I can take the 4 as the square root of 16 and multiply it by the square root of 5. Well, the square root of 5 doesn't have a square root that is real simple and a whole number, so we're just going to leave our answer just like this. So the idea is finding a factor of the number that is a perfect square. That helps things go along a little bit more quickly. And of course you can multiply these two numbers together, so 6 times 21, anything under the square root symbols can be multiplied together, and that is going to be 126. And then the factors of 126 may take you a little while, unless you have your handy-dandy multiplication chart with you. And that can be broken down into the square root of 9 and the square root of 14 because those two are factors of 126. Nice thing is square root of 9, the square root of it is 3, so we don't need the square root symbol anymore. And square root of 14 doesn't have a perfect square or square root, so we'll just leave it as 3 root 14. And if we take a look at C here, we can make this into two separate square root problems, one on the top, one on the bottom. What's nice about this one is that both of them are perfect squares. So the square root of 4 is 2, the square root of 81 is 9, so we no longer need the radical symbol. We can just leave our answer as 2 over 9. Okay, I'll let you try D and E, and let's take a look at F together. Just want you to remember that you can multiply the things that are in front of the radical symbol, so we're going to end up with 15, and then we're going to multiply the things underneath the radical symbol, which is 240. All right, so I'm going to have you figure out numbers that multiply to 240, and I would like you to finish problem F as well as problem D and E. All right, so why do we need to know about square roots when we've been working on quadratic equations? Well, we're going to solve a quadratic equation using square roots. Now, you can only use square roots to find x-intercepts when your equation is in standard form. So you're going to be looking for a standard form. However, b is going to be equal to 0. So you will not have that term with the x with it. Okay, so you're just going to have an x squared plus a constant. And the other time that you can use the square roots to find x-intercepts is going to be when you are having a quadratic equation in vertex form, when we have our h and our k. All right, so let's take a look at an example problem. Now, if you had y equals 9x squared minus 81, you might recognize this as the difference of two squares. So I'm going to show you two different methods. If we factor this by using our difference of two squares method, then we will most likely have a 9 out front because we're going to pull a 9 out of the first term and a 9 out of the second term, x squared minus 9. And then we would break that part down, right, the part inside, to x plus 3, x minus 3, because we want to have, we're using our knowledge of difference of two squares. And then if we set this part equal to 0, and this part equal to 0, then we would see that x is going to be either 3 or negative 3. Okay, so if we use our factoring method, we get that answer. And then I would like you to find the new method, which is what we were going to do right now. New means that we're going to be using square roots. Okay, so the factoring method is kind of our old method. Does it work? Absolutely. Can you use it anytime you want? Yes, unless the directions on your assignment or quiz tell you to use the square roots method. All right, so let's take a look at this where we can set the equation equal to 0. I'm going to add 81 on both sides. All right, so that cancels that, and 81 is now equal to 9x squared. Well, if I divide both sides by 9, I'm going to get x squared by itself. Okay, so I'm going to have x squared equals, what's 81 divided by 9? It is 9. Now, if I take the square root of both sides, let me take the square root of this side and the square root of this side. This ends up being just x. This ends up being plus or minus 3. Well, what do you know? These two are the exact same. Okay, so it's a preference really. Do you want to use square roots because you find that easier, or do you like the factoring method that we did, several lessons ago? And as long as it doesn't say which way you have to do it, feel free to use either method. Okay, example 3 is up next. We're going to be using square roots if possible. So what I'm going to do is 3x squared plus 5 equals 41. I would like to have all of my x squared terms on the left, and I'm going to subtract 5 here because I'm going to try to use square roots if I can. So that's going to cancel. I have 3x squared over here still, and I have 36. Now, looks like to me we have the ability to divide both sides by 3 because that will cancel that. I'm trying to get x squared by itself. X squared equals 12. Well, unfortunately, 12 is not a perfect square of any number. However, if we take the square root of both sides, I can say that this side is going to be x, and this is going to be the square root of 12. However, if I break that down a little bit, x is going to equal plus or minus the square root of 4 times the square root of 3. So if you recall, 4 times 3 is 12, and 4 is a perfect square, which is why I wanted to use that. If you use 6 and 2, that's just not going to work out very nicely. So I'm going to try to pick factors that have an actual square root that I can use. So x is going to be equal to plus or minus 2 root 3. The 2 came from being the root of the square root of 4. So my final answer is this right here. All right, on the last page of your notes, I would like you to do example number 4 on your own to try that out. And I'm going to finish up with examples 5, 6, and 7. So for example 5, let's take a look at it. 2x squared minus 7x equals 0. Well, right now, all I can see is that I have an x. I can say 2x minus 7, but I'm not going to be able to use anything in terms of square roots because nothing here is a perfect square. There's no way for me to take the square root of anything here. So this one actually, notice how it says if possible, this is not possible. And just another note is it's not possible because there is a b, and it's negative 7. So when b is not equal to 0, we're not going to be able to use the square root method. All right, moving on to example number 6. Now this one looks a little bit more complex. Let's take a look at what we can do to simplify it a little bit. The first thing I notice I can do is subtract 7 on both sides. So I'm going to end up with negative 1/5 times z plus 3 squared equals negative 7. to get rid of my fraction out front, I'm going to multiply by the inverse. So multiplying by -5 over 1, and that's going to be multiplying this by -5 as well. And the reason I put the over 1 is just to make it simple to see that that's going to cancel here. So I end up with z plus 3 squared equals positive 35 because I'm multiplying two negatives together. And now I want to take the square root of both sides. All right, so here's my attempt at doing that. And I'm going to say that, let's see, this is going to end up being z plus 3 because the square, when you have something that's squared like that under the square root, it just leaves it, whatever was trying to be squared is going to be what comes out of the square root. Okay, so we were able to take the square root of the left. We were not able to take the square root of the right. However, we can subtract a 3 from this side and subtract a 3 from this side. So our final answer is going to be z equals -3 plus or minus the square root of 35. That one's a little bit long and complicated. So if you'd like me to go over that one again in class, just make sure you ask. All right, finally we have example number 7. The first thing I'd like to do with number 7 is add 45 to both sides. So in that case, we have 5 times x minus 4 squared equals 45. And to simplify things a little bit more, I'm going to divide this side by 5 and this side by 5. That gets rid of that. So x minus 4 squared equals 9. So if I take the square root of both sides, when I take the square root of this side, it's just going to leave what's inside the parentheses, because remember, when you have something that's squared, it kind of cancels out the square root. So x minus 4 equals, and by the way, I'm going to take the square root of this side as well, and that's going to be plus or minus 3. Now we have two separate problems here because we have a plus and a minus 3 on the right. So if I add 4 to this side and add 4 to this side, I'm going to end up with either x equals 7, because positive 3 plus positive 4 is 7, or x equals 1, because I would be looking at 4 plus 3. So over here to the side, I'm going to show you why this was 7. It's going to be 3 plus 4, and this would be 4 plus a -3. Remember, if we end up using the -3 plus 4, that would result in positive 1. So a lot of times when we're working with square roots, we're going to end up with two answers, and that's because there's a positive result from a square root and a negative result from a square root. And what I mean by that was that plus 3 and minus 3 are real possibilities of square roots of 9. All right, so again, you're supposed to be looking at finishing up example number 4, and remind yourself to write down any questions that you have, and I can answer those in class for you.